If you paid attention to some of your science lessons in school, you may have heard of a metabolic process known as respiration. And when you were taught about this inside of school, especially sort of secondary school, primary school, when you're sort of learning the basics of how the world works in a way, you were told of this chemical reaction that is used to produce a lot of energy inside of the body. Glucose plus oxygen then reacts to form carbon dioxide and water. And if you want to sort of balance chemical formula, molecular formula reaction, C6H12O6, which is the chemical formula for glucose, plus 6O2, which is molecular oxygen, goes and reacts to 6H2O, which is water, plus 6CO2, which is carbon dioxide. Now, while this is very true, it is also a very vague way to sort of put the process of respiration, which is actually a lot more complicated than you may think. It contains around 4 different main metabolic processes that are used to produce energy. One of them is the thing that produces the majority of the energy, but a lot of the other stuff is the stuff that's a little bit more easy to understand and can be quite nice for those who have sort of pattern and logic-based brains, processing brains, where getting from event 1 to event 2, or molecule 1 to molecule 2 in this instance, is quite a nice and interesting pathway and process for your brain to sort of understand, and it can also be quite useful just to expand your knowledge as a human being. Because as I said before, with this sort of glucose plus oxygen goes to carbon dioxide and water, because glucose doesn't literally chemically combine with oxygen to form carbon dioxide and water, but there are actually 6 different metabolic processes that are used inside of the body to actually produce energy for you to function like a normal human being. And that is the digestion and metabolism of every single macronutrient that your body can process. And there are 4 of these, all containing different amounts of calories per gram: fats, alcohols, which you may not have previously known about, carbohydrates, and proteins. Fats can be metabolized by the body, and this produces 9 calories per gram of energy. Alcohols can actually be processed by the body, and this produces 7 calories per gram. Carbohydrates is 3.75 calories per gram, and protein is 4 calories per gram. Now, all of these molecules pretty much end up sort of turning into acetyl-CoA, a mega molecule. I mean, proteins is a little bit more complicated. It can end up turning into a few other intermediates that can then be used in things that acetyl-CoA ends up making in some of the processes that I'm going to talk about now, as well as in later videos in more detail. But all these 4 macronutrients essentially can be digested and metabolized to form a base molecule known as acetyl-CoA. I know I said about the whole 4 metabolic processes that occur in the start. That only really applies to the sort of glucose reaction, but you could technically say fats plus oxygen equals carbon dioxide plus water. You could technically also say proteins plus oxygen equals carbon dioxide plus water. You could technically say alcohol plus oxygen equals carbon dioxide plus water, because they all sort of end up forming a few of the base molecules that end up being used to sort of actually get things like the CO2, the H2O, and we'll discuss all of this towards the end of the video. But trust me, it will all make sense eventually, because I don't want to overcomplicate it for you immediately. While the equation that I previously stated is a very, very vague one, it's quite a big jump up from a very, very vague reaction that's 1 step to there being around 20 to 30 steps in the sort of actual respiration process. Acetyl-CoA is a sort of baseline molecule of a lot of the metabolisms of the macronutrients, and acetyl-CoA is an energy storing molecule. The amount of acetyl-CoA that fats, proteins, carbs, alcohols can actually produce essentially dictates the amount of calories per gram this macronutrient has, and fats are the thing that produces the most acetyl-CoA out of all the macronutrients, hence why it ends up having the most calories per gram of energy produced whenever you consume it. But acetyl-CoA, during a respiration process known as the Krebs cycle, ends up being broken down to sort of release the energy that is stored inside of its molecular carbon-carbon bonds. Now, the Krebs cycle is sort of a circular reaction that ends up releasing carbon dioxide during a few of its reactions. Now, that is very, very interesting, because I mentioned the sort of glucose plus oxygen, carbon dioxide and water. The glucose, I mean, while it can apply to things like fats, proteins, and alcohols as well, if we're sort of just taking glucose as an example, glucose can be broken down into things like pyruvate and then acetyl-CoA after that. But then acetyl-CoA, as I've said, gets fed through the Krebs cycle, producing CO2 molecules. So now we've got the glucose. We know that the glucose goes through the process of glycolysis to produce pyruvate, to produce acetyl-CoA, that goes into the mitochondria to do the other respiration processes like the Krebs cycle to produce CO2. So we've got the glucose ticked off, we've got the CO2 ticked off, but where does the O2 and H2O actually come from? Where does the oxygen come from, and where does the water come from? But as well as the Krebs cycle producing carbon dioxide, it also produces a lot of high energy storing molecules such as ATP, NADH, and FADH. And one singular Krebs cycle produces one each of these molecules. One acetyl-CoA molecule can go through the Krebs cycle, end up turning into oxaloacetate, and through that process you get one NADH, one FADH, and one ATP. And then oxaloacetate can recombine with acetyl-CoA to form citrate, and the cycle then ends up continuing until you run out of acetyl-CoA or one of the enzymes or whatever. But that's pretty much unlikely to happen because that would cause your body a lot of damage. But these NADHs, FADHs that I mentioned earlier can then be used during the electron transport chain, which is the most energy yielding process of the respiration, but it's also the most complicated and one that I am still learning and still yet to fully understand. It's very, very complicated, but it all has stuff to do with a lot more chemical stuff, which I am a lot more interested in than the kind of biochemistry side of things. It's got a lot to do with H+ protons, things such as electron carriers, but essentially the NADH and the FADH will sort of end up going around a little chain, an electron transport chain, donating its electrons to other carrier molecules with a slightly lower energy, and this will end up yielding ATP from these reactions. And while things like glycolysis produces 2 ATP molecules, the Krebs cycle produces maybe around 1 ATP molecule. I think, yeah, it is 1, as I said before. Oxidative polarization, the electron transport chain, produces around 36 molecules of ATP. But I mentioned before about oxygen and H2O still not being involved inside of the process of respiration, but this is where oxygen and H2O actually end up getting involved. Glucose, in this sort of example, ignoring things like fatty acids and proteins and alcohols, ends up going through the glycolysis process, going through the Krebs cycle, and we've still not added it and all its intermediates and all the things that can be produced from it to oxygen. But that is where this changes. The electron transport chain, the final electron receiver, electron acceptor inside of the electron transport chain, which signals the end of the electron transport chain, is oxygen. And that means that when oxygen accepts this electron, it ends up converting into water, and that completes the reaction. You have glucose go through all of the different really complicated metabolic processes to end up being yielded into things like NADH and FADH. That ends up going through oxidative phosphorylation, gets the electron that's inside of the NADH molecules, ends up being added onto molecular oxygen as it's the final electron acceptor, and that will convert it to molecular water. C6H12O6 plus 6O2 molecular oxygen. It goes in like a little arrow, and then it ends up going to 6H2O molecular water to 6CO2 carbon dioxide. The reason these molecules have like a 6 in front of them is simply to balance out the chemical reaction. Even though this chemical reaction isn't simply like one and done, it doesn't, as I said, glucose doesn't actually chemically combine with oxygen itself. It goes through loads of other processes, as I've stated in this video and other videos, before it can actually end up being converted and added to oxygen and then converted to carbon dioxide and water, which is all a whole interesting thing. I've done a load of other videos on things like glycolysis, and I'll do future videos on really in-depth things about acetyl-CoA, the citric acid cycle, so I highly recommend subscribing and sticking around for that. But I appreciate it if you stayed for this long, and I also recommend subscribing because I love this community of young tribal people who are willing to improve themselves so much more than they already have, and good luck.